Hello guys, welcome back to the Black-Scholes Merton European Option Pricing Derivation video lecture series. And in the previous video, we discussed uh, the desire to find an equation for S of t such that it represents a set of stocks S1, S2, S3, all the way to S of n, with a singular equation with parameters that can be calibrated. So to start this off, I want to draw a representation of what exactly we're trying to analyze. A singular stock. So we're going to have a time axis. We're going to start at an initial time t0, and this is going to be our stock price as a function of time. So what do we know about a stock price? Well, it has a starting position, or the time we want to analyze. We could call this SO. And it has some kind of movement. This movement is what we're so interested in. And let's call this our stock price as a function of time. Cool. So to start our model, we can notice one very evident characteristic of this movement, such that it has some kind of drift, or some kind of slope, such that we have, try it again here, we have a delta time and a delta s. Cool, so we can represent that as a mathematical equation, right? We can say our delta s over delta t is going to be equal to a slope. Now, for every stock, there's going to be, at every time increment, there's going to be a different slope, right? A stock that tends to go up will obviously have a positive slope. A stock that tends to go down will obviously have a negative slope. So this could be one of the parameters that we can calibrate. And we can call this mu. And we're going to say this is going to be our mean returns. So without all the words, let's rewrite this as delta s over delta t is equal to mu. Cool. And then we can rewrite that as delta s is equal to mu delta t. Okay, now we have this equation right here, and to do analysis and to further extract information from this equation, we can rewrite this in a differential form, such that we can utilize the power of calculus to draw more relevant information from that. So in differential form, we can represent this as ds is equal to mu dt. Cool, and just another way to write that, we know that ds over dt is going to be equal to mu. Now, focusing on this again, we can integrate both sides, and clearly we'll have s plus some constant, c1, is equal to mu t plus some constant, c2. Now, c2, some constant, minus c1, which is another constant, is obviously going to be some constant, right? So I can rewrite this whole thing as S is equal to mu t plus C, where we're going to have some kind of drift, and this is going to be our starting. Cool. Now, in the model we drew, we have a starting point, which we're going to denote as S0. So if we just plug that in, we can have our stock price as a function of time is equal to mu t plus S naught. Cool. So this is going to be our initial very simple model, and this is going to be in non-differential form, though I am interested and more interested in this form, just because we're going to be building on top of this model. But for now, this is going to be what our model looks like. And this one right here is obviously easier to graph, so we will do that. Okay, so we know that we're going to have some starting stock price. Let's say this is S0. Depending on the stock we're trying to analyze, this can obviously be a different starting constant. And then we're going to have some mean returns. Right? So this is going to be our delta t and delta s, which is essentially going to be our mu. Cool. And in this specific case, we know our mean returns for the stock we're analyzing is going to be greater than 0. We could also have a negative mean returns. So this is going to be mu is less than 0. Now there's an obvious problem with this. Our stock price must be in the range of 0 to, let's say, infinity for now. It can't really be infinity because of a limited money supply and other economic factors. But the more important part is it can't go below 0. It defaults at 0. So how do we fix this problem? Okay. Now I'm going to denote this as problem number 1. And another problem is as follows. So this is going to be problem number 2. And you'll see how both of these problems can be fixed by adding one small aspect to our model. So this is going to be problem number 2. Mean returns is in percent form. So what that means is if, let's say, my mean returns is going to be 0.01%, and my initial stock price is going to be at 100, then at T0, my stock price will be, or let's not say T0, let's say at my first time index, my stock price is going to be 100 plus 1% of 100. So that's going to be $1, so that's going to be 101. But if my stock price started at 1,000, then at T1, I would have 1,000 plus 10. So these are different. So what does this mean? This means our mean returns is actually scaled by our stock price. Now, if I were to take T2, for example, then I would take 101 plus 1.01, right? And if I take T2, I would have 1010 plus 10.1. And I can continue this so on and so forth, right? Just to further my example. But this is going to be our important conclusion right here. So, two problems. Negative stock prices and our mean returns is actually going to be scaled by our stock price itself. So, we're going to focus on problem number 2 first. And you'll see how by fixing problem number 2, we'll actually fix problem number 1 implicitly. So here we're going to improve our model. And we're going to do exactly what we said. And we're going to start with our differential form. We know ds is equal to mu dt, but we have to scale by s, right? So we're going to rewrite this as ds is equal to s mu dt. So now this is essentially going to be our slope. Cool. Now this is another differential equation that we can so solve. So to rewrite it, we can say ds is equal to mu s dt. I can divide both sides by s to cancel s out on this side. And what this will give me is ds over s is equal to mu dt. The same way I can integrate both sides. And ds over s is obviously going to be the natural log of s plus some constant c1. And then that's going to be equal to mu t plus some constant c2. Cool. Now, like we said before, we know that c2 minus c1, when we do that step, is going to be some constant c. So let's perform that, and we will see that ln s is going to be equal to mu t plus some constant. And we've also concluded that our constant is going to be S0 by previous analysis. So our final equation is actually going to be ln s is equal to mu t plus our initial stock price. Cool, so how do we solve for s? Well, we can raise both sides to the power of e. And what this will do, our e and ln will cancel out, which will give us this. So we'll have s as our function of time. It's going to be e to the power of mu t plus s naught. Okay, cool. Now, we can do e to the power of mu t times e to the power of s naught. And actually, small mistake here. Let's not make this c is equal to so, s naught substitution right here. It's just yet. Let's just keep it as c. That was a mistake on my part. So if we have something like this, then we know that e to the power of c is also just going to be some constant, and this is going to be the constant that we're going to take as s naught. So essentially what we have is s of t is going to be, I'll write that a little lower, s of t is equal to e to the power of c is a constant, which we're going to say is the initial stock price. So that's going to be S naught times e to the power of mu t. And to confirm this, if we take S of 0, for example, then we'll have our initial stock price, e to the power of mu times 0, which is, so it's going to be S of 0 times e to the power of 0. And we know that e to the power of 0 is equal to 1. Therefore, our stock price at position 0 or time equals 0 is going to be our initial stock price. So that checks out. Cool. So let's graph this. Now, we've concluded that we fixed our initial problem, or problem number 2, which is the fact that our mean returns is a percentage, so it has to be scaled by our stock price itself. So we know that problem 2 is checked off. But what about problem number 1? So if this is our initial stock price, then we know as a consequence of problem number 2 that our stock price is actually going to be geometric. So let's say this is stock price 1 with mean returns greater than 0. Now, our model is e to the power mu t. This is going to be what we're focusing on, right? And an exponential function actually has an asymptote at y equals 0, or in this case, s of t is equal to 0, or our stock price is equal to 0. So if we have a negative mu, we're going to have an exponential decay such that it reaches the constant S naught is equal to 0. So it can never cross the S is equal to 0 axis. So it can never become negative. So we actually fixed problem 1 implicitly, such that now we have a stock price that's in the domain 0 to infinity. Cool, so now we essentially modeled the general movement of S of t. And obviously, first let me write it down. We concluded that S of t is equal to the initial stock price, e to the power of mu t. And in differential form, we have ds is equal to mu s dt. So this is going to be very important. And this is going to be our general movement of our stock price. Now, the next thing we have to add is going to be our shock, so to say. So if this is our initial stock price, we can have, let's say, 2 kinds of movements, but there's some kind of randomness associated with this general movement. So modeling these kinds of movements, these random shocks, is what we will be discussing in the next video, and this is where we will need something called Brownian motion.